Alright everyone, today we're talking about 5.1c, and that is angles and their measurements. So we're still in this section. This is the last one of 5.1. Today we're going to be focusing on spinning objects. We're talking Ferris wheels, we're talking clocks, we're talking merry-go-rounds, anything that spins and has motion in a circular manner, I guess, or circular path. Alright, so we're going to talk about linear and angular velocity of rotating objects. Velocity. Let's start with velocity. Velocity is the speed of something in a given direction. So when I'm talking about velocity, I'm talking about a speed of something in a given direction. Well, when an object is actually traveling around a circular path, they actually have two different types of velocities. The first one is a linear velocity, and that is the rate at which the object moves or travels along a circular path in 1 unit of time. Linear velocity is measured in linear units like miles per hour. The next one is angular velocity. Angular velocity is the rate at which the object rotates or turns about a fixed point in 1 unit of time. Angular velocity is measured in angular units like revolutions per minute. Now, those two can seem very similar at times, and so example 1, we can hopefully get to the root of why they're different and why they even use different units. So example 1, we have a carousel. We have a carousel with 2 horses on it. We have a black horse, and that is 1 meter from the center, and we have a white horse, which is 2 meters from the center. So if we look at this picture over here, we can kind of picture the top-down view of it. Note that the white horse is further out than the black horse. So the black horse is closer to the circle. When we talk about merry-go-rounds, so to go all the way around, say it takes 2 minutes. It takes 2 minutes for the merry-go-round to go all the way around. Well, that means it takes 2 minutes for this white horse to go all the way around. And it also takes 2 minutes for this horse to go all the way around. If the merry-go-round is spinning and both horses are fixed to it, depending on how it's spinning or how long it takes to spin, they're both going to take the same amount of time to spin. So that's going to lead us to the first question. It says, which horse has the greater angular velocity? Which one has the greater angular velocity? So let's go back up and ask what angular velocity is. Angular velocity is the rate at which an object rotates. An object rotates. So what they're asking for is, how long does it take for the white horse to get around versus how long does it take the black horse to get around? Well, they're both fixed to a circle. They're both fixed to a circle that has a fixed rate of time. So if it takes the white horse 2 minutes, like I said before, to get around, it's going to take the black horse also 2 minutes to get around. It's a fixed circle, so it's going to take the same amount of time to get around. So we're talking about angular velocity. They're going to have the same rotational speed. It's going to take the same amount of time for each one to get around. So in fact, they have the exact same angular velocity. So they have the same. They have the same angular velocity. It will take the same amount of time to make 1 revolution. Each one, it will take the same amount of time to make that 1 revolution. So it will take the same amount of time to make 1 revolution. Remember, 1 revolution is 360 degrees. So like I said, angular velocity is measured in how long does it take to get all the way around. It'd be 1 revolution per minute, 2 revolutions per minute, something with revolutions, which means we're dealing with degrees and we're dealing with radians, depending on if we're degree or radian world at the time. All right, now it says which horse is traveling the fastest, the linear velocity. So linear velocity is actually the speed at which it's going. So we already said in my example before, it takes 2 minutes for this to get all the way around. So we're going to say this takes 2 minutes to get around. Its angular velocity is 1 revolution, I guess, per what did I say, 2 minutes? 1 revolution per 2 minutes. Well, which one has to move faster to obtain that speed? So we know it takes 2 minutes for each one to get around. Well, let's look at the white horse. The white horse has to, in 2 minutes, travel that distance. In that same amount of time, the black horse has to travel this much distance. So the white horse has to travel a lot further in the same amount of time as the black horse. So the white horse, in linear velocity, is moving faster than the black horse. They're rotating at the same speed. They still take 1 revolution per 2 minutes, but the white horse is going to have to, linear velocity-wise, move at a much quicker pace to cover up that extra ground. So it's going to be the white one is moving the fastest. The white horse. So how I worded it is basically it's the white horse. It covers the greatest distance in the same amount of time. So linear velocity is almost like you're focusing on, you're not really caring that it's moving around a circle, it's just the speed at which it must attain to make that circle. Angular velocity is rotations, linear velocity is like miles per hour, your feet per second, so on and so forth. So I think of linear velocity more of a straight, we're going straight along this line, where rotation is that fixed rotation. All right, that's going to lead us to 2 formulas. We have a linear velocity formula, and we have an angular velocity formula. All right, let's start out by talking about the linear velocity. The linear velocity is basically velocity equals s over t, where s is the distance traveled by an object, and t is going to be our time. So it's distance traveled divided by time is going to get your velocity. Velocity can also be this formula, which we'll get back to in just a second. So let's go over to the right and talk about angular velocity. Well, angular velocity is, and that's omega. So angular velocity is omega equals theta over t. We already know that t is your time. That t is our time. Well, what's that theta? Well, theta is always going to stand for angles. In pre-calc, we'll always use theta to stand for an angle that we don't know of yet. So theta is the angle of rotation. And get this, it's in radians. It is in radians. So we're going to go to radians anytime we're dealing with angular velocity. It just doesn't work with degrees. It's not the way it's set up. All right, so we're going to do in radians, and the object moves about in time t. So same thing there. So this one is basically angle divided by time. It's very similar to distance divided by time of velocity, except we're switching out distance with time. All right, so those are our basic ones we're going to use. Now, if we happen to know either one of them, so let's look at this formula over here where velocity equals r times omega, or r times your angular velocity. This would be if you actually knew your angular velocity. So if you know your angular velocity, you can use this formula. And that is a radius, that r stands for our radius, times our angular velocity will give you your linear velocity. So if you ever know your angular velocity, you just got to multiply it by your radius, and you come up with your linear velocity. Likewise, if you happen to know your linear velocity, we can say angular velocity equals your linear velocity divided by your radius. So to go from your angular velocity to your linear velocity, you multiply by your radius. To go from your linear velocity to angular velocity, you divide by your radius. So whenever you find one of these, you shouldn't have to, unless you don't know the radius, you shouldn't have to do the inside formulas. But you do have to know your radius. So generally speaking, if you're looking at the problem and they give you the radius, they're probably looking for you to do one of these two somewhere along the line. All right, the first problem we're going to do is example 2, and that is Adam the ant sitting on the second hand of a clock. That's 12 centimeters from the center. So like I said before, when we read these questions, I'm looking to see if they give us a diameter or a radius. And right off the bat, it says it's 12 centimeters from the center. So Adam the ant sits on the second hand of a clock, 12 centimeters away from our center. If you're 12 centimeters away from a center, you are talking about your radius. A radius is the distance to the center. Okay, the first question is, what is his angular velocity in revolutions per minute? So our angular velocity, if we look at the other slide, or if you go back in the video, is going to be omega. Let's go ahead and do this. It's going to be omega equals theta over time, where theta is our rotations over time. Well, now we have to do a little bit of thought process here. Okay, sitting on the second hand of a clock. So some of these we have to come up with our own rotations per time. So a second hand on a clock, well, that goes around once every minute. And it asks for revolutions per minute. So it's going to be 1 revolution per 1 minute. That's it. That is our angular velocity. The other way we can write it is 1 revolution per minute. You can do that too. So 1 revolution every minute. Our next one asks, what is his angular velocity in radians? In radians per minute. All right, so let's go back. Let's go back at where we are right now. We are at revolutions per minute. So we have our angular velocity is 1 revolution per 1 minute. Okay, so we have to get from revolutions per minute to our radians per minute. Well, 1 revolution is just 2 pi. 2 pi is 360, 2 pi is 1 revolution. So we're going to do a little bit of unit conversions here, where I want revolutions to turn into radians. So we're going to multiply that by 2 pi in every 1 revolution. That way we're canceling out our revolutions and we're left with 2 pi radians. So that's going to equal 2 pi. Remember, we should really think about that as radians over 1 minute, which we could rewrite as 2 pi radians per minute. If it asks for an approximate, because a lot of times if you're talking about speed, you usually want to give it like a little more approximated form. Sometimes it'll say round to the nearest hundredth, which in this case would be 6.28 radians per minute. But in this case, we're going to really focus on this one. All right, so let's go back on what we just did. We first found the angular velocity, which most of the time is going to be the easy thing. How many revolutions does it do over a certain number of time? And then we're almost always going to multiply that by 2 pi over 1 revolution to put that into radians. So we almost always do these 2 steps back to back. So we find our rotations per minute, multiply it by 2 pi over 1, and we will have it in radians per minute. That will happen so many times. If you just recognize that pattern, it makes your life so much easier. All right, let's continue on. It says, what is his linear velocity in centimeters per minute? So let's go to our linear velocity. Look at your linear velocity formulas. You have 2 of them. In fact, let's go back to it. We have 2 of them. We have, if you know the distance and the time, you can go that way, or if you know the radius and the angular velocity, you're going to use the other one. Well, nowhere in the problem does it say anything about distance. So we actually don't know the distance offhand right now. So we're probably going to use the other one because we know the radius and we know the angular velocity. So we're going to go with our linear velocity equals our radius times our angular velocity. In this case, we said the radius is 12 centimeters times, and we are going to have our 2 pi from up above. In fact, let's do it like this, 2 pi radians per 1 minute. Now, here's what's happening here. Here's what's happening here because we're going to be left with centimeters. And how does that happen? Well, if we're talking about the radius, remember what radians are. 12 centimeters is actually going to be the distance of 1 radian. So if you're really concerned about how things cancel out, you can write this down to let yourself know that the radians cancel out. And you're going to be left with 2 pi times 12, which is going to be 24 pi centimeters per 1 minute, still on the bottom. Which we could rewrite as 24 pi, centimeters per minute. Or, like I said, a lot of times you are going to approximate it, especially if you're giving centimeters per minute. Usually you don't leave pi in it, so a lot of times you're just going to approximate it to 75.40 centimeters per minute. So if I was asked to give an answer, I'd probably approximate it. And if I needed to use that 75.4 in another problem, I'd probably use the exact 24 pi. So if I was just giving an answer, I would most likely round it. I would read the directions first, and then I'd probably round it, because usually we give things in centimeters and decimals, not in pi. If I needed to use it in part of another equation, I'd probably stick with the exact form. So there's no 100% guarantee this is what I want every single time. Look at the directions. If I don't give you directions, do what you will with either one of them. But usually if you're plugging in a formula, you try to leave it as exact as you can until you get to the end, and then you approximate it. All right, let's go down to the next thing. Next thing says Adam crawls to a point 5 centimeters from the center. What are his angular and linear velocities now? Well, angular velocity, let's handle that first. Our angular velocity is going to equal basically how many revolutions does it take per minute. Well, if him walking out further from the center, but he's still in the second hand still takes 1 minute to do 1 revolution. So your angular velocity is not going to change. So we're going to stick with that 2 pi radians per minute. It's still going to take the same amount of time to go around. Still going to take that 1 minute to get all the way around. Still takes 1 minute for revolution. All right, our linear velocity will change though because our radius changed. So Adam crawls to a point 5 centimeters from the center. So he's 5 centimeters from the center right now, which means your radius is now 5 centimeters. That is our radius. The formula is take the radius and multiply it by our angular velocity. Our angular velocity is that 2 pi radians per minute. Remember from looking up above, our radians are actually canceling out. I'm not going to show it this time. I'm just going to stick with, that would be 10 pi, and we'd have centimeters per minute because our radians are really canceling out. There'd be radians down there that would cancel out. All right, like I said, if I'm using that later on, I would keep it, but more than likely, I'm just going to round that if that's my actual answer of 31.42 centimeters per minute. So it's really okay to have pi up in your angular velocity, but usually when you're talking about your linear velocity, you try to round it. You don't leave a pi in there. All right, the very last thing we have is Adam the ant crawls to the very center of the clock. What are his angular and linear velocities now? Now, you might think his angular velocity is 0, but he's still spinning. So if he's just standing on the center of the circle, how long does it take him to do a full 360? Well, it's still that same 1 minute. He's on the second hand, so it'll take him a minute to spin all the way around. So your angular velocity is not going to change. As long as he's on that second hand, it will always be an angular velocity of 2 pi radians per minute. The only way that would change is if he went to the minute hand or the hour hand. All right, his linear velocity, though, he's not traveling anywhere. He's just spinning in a circle. So our answer should be 0. And you could confirm that mathematically by saying, okay, the radius is 0. He's 0 centimeters from the center. Multiply that by your angular velocity, and you're going to come up with 0 centimeters per minute. which is what we thought. He's not covering any ground, he's just spinning in a circle. All right, the next thing we're going to cover is example 3 is what are the angular velocity in radians per second and linear velocity in miles per hour of the trip of 22-inch lawnmower blade that rotates at 2,500 revolutions per minute. Stop there. So a lawnmower blade with 22 inches. So if we're talking about a lawnmower blade, it looks something like maybe like that. And that whole thing is 22 inches, so its radius is going to be 11-inch radius. Just so we're on the same page. So we're talking about 11-inch radius. All right, angular velocity. Angular velocity. Almost every time you're going to find angular velocity, you're going to start with revolutions per something, per minute, per hour. So we look up there and it says there's 2,500 revolutions per minute. So that is the start of our angular velocity. So we have 2,500 revolutions per 1 minute. Well, it says what are the angular velocities in radians per second. So I want radians per second. So I don't want the revolutions and I don't want the minutes. So the first thing I'm going to do is I'm going to get rid of the revolutions. And that's by multiplying by 2 pi. There are 2 pi radians per 1 revolution. Your revolutions will cancel out and you're going to be left with 5,000 pi radians per 1 minute. All right, now we have to get rid of the minutes because we need to have it in seconds. Well, to get rid of minutes, we need to have minutes up here so that they cancel out, and I'm trying to make it into seconds. So even before putting anything in there, I know those minutes are going to cancel out because minutes on top of minutes cancel out. Now I just got to see how many minutes per second. Well, there's 1 minute per 60 seconds. Now in this case, we're talking about revolutions per minute, per hour, per whatever. So I'm going to go ahead and I'm just going to approximate it. So it's a weird number. It's 5,000 over 60, which you can reduce to 500 over 6, but it's a weird fraction. So I'm just going to reduce it down and simplify it to 261.80 radians per second. It doesn't say I can round it or not round it, so I'm going to just go ahead and I'll round it. And we'll move on from there. All right, next one is what is our linear velocity? Well, once you know your angular velocity and your radius, linear velocity should be a breeze. Because linear velocity is just your radius, which is 11 inches, times your angular velocity, which is 261.8 radians per second. Quick reminder, we are really doing 1 inch over 1 radian. So our radians will cancel out, and we'll be left with inches per second. So we're going to do 11 times 261.8, which is going to be our 2879.8 inches per second. Cool. The last thing we need to do is we need to convert that to miles per hour because it did ask for a linear velocity in miles per hour. We have a linear velocity, it just happens to be in inches per second. So we need to change the inches to miles, and we have to change the seconds to hours. So let's go ahead and do that. So we're going to convert to miles per hour. So we're starting with 2879.8, and we have inches per 1 second. Let's start with the inches. I want the inches to become miles. So first of all, I want the inches to cancel out. So we're going to put inches on the bottom. And the easiest thing to convert that to, first of all, is feet. Because there are 12 inches in 1 foot. So now we cancel out our inches and we are left with feet on the top there. I don't want feet, I want miles. So we're going to go, well, feet can convert to miles. There are in fact 5,280 feet per 1 mile. And now our feet would cancel out and we'd be left with miles on top. Now the only thing we have to worry about now is our seconds. So I'm trying to figure out how many seconds are in an hour. Well, we can either go through seconds to minutes to hours, or we can go straight from seconds to hours because we can figure that out. So there are 60 seconds in a minute, and there's 60 minutes in an hour. So there are 3,000. Ooh, I put it on the wrong thing. If you look at it right now, my hours and seconds wouldn't cancel out. Nothing would cancel out. I'd actually have seconds squared. So I need to flip that. I need to always have what I'm trying to get rid of on top of the other one so our seconds can cancel out. All right, there are 3,600 seconds in 1 hour. Now if we look at it, everything is crossed out except for miles and hour. So now what we're going to do in your calculator is you're going to multiply all of this out. Which if done correctly, you should come up with about 163.6 miles per hour. All right, one more example. We got a Ferris wheel. We got a Ferris wheel with a radius. Ooh, they already give us a radius. 50-foot radius. Awesome. Makes 1.5 revolutions per minute. The first thing we have to do is find the angular velocity of the Ferris wheel in radians per second. So we're going to start with our angular velocity equals 1.5 revolutions per 1 minute. We're going to convert that to radians by multiplying by 2 pi in essence. Radians per 1 revolution, which is going to equal 3 pi radians per 1 minute, because the revolutions would cancel out. And so we're almost done, because it actually wants it per second. So we do need to make it into per second, so we're going to put our minutes over our seconds, so our minutes cancel out. We have 60 seconds in 1 minute, which is going to result in 3 pi radians per 60 seconds, which if we just approximate that, that would be about 0.16 radians per second. All right, the last thing we have to do is we need to put that linear velocity in feet per minute. Well, linear velocity is radius, which is already 50 feet, times our angular velocity, which is 0.16 radians per second, which is going to be about, because we're approximating everything,